All right, now let's talk about higher order factorization machines. So basically, these are pretty much just the same thing that was defined in the previous factorization machine paper. There is a little bit different notation in this paper, and I'll probably mention this a few times, but I love the notation in this paper. There's a lot of things that they do, just like very subtle notational choices that make a lot of sense. So let's see here. Let's get on the same page with the notation because some of it is a little different. So the input vectors here, instead of being an Rn, they're going to be an Rd. And so for the weights, obviously there's the weights that are in Rd, and they're called W like they were in the previous paper. But here, instead of like the vector or the matrix of the vectors in the previous paper, it was called V, and it was a n by k matrix. Here it's called P, and it's a d by k matrix. By the way, I really like the notation here where the rows of the matrix P are denoted by Pj with the over, and there's an overline on top of the P, and that sort of makes sense because like a row is just sort of like a line, like a horizontal line, and so there's a horizontal line above this letter, so it makes sense. Like you look at it and it makes sense to you. And so columns, we'll just call them P sub S, so it's just lowercase p in bold without it, the overline. And then the indices, this I'm not as familiar with this notation, but I really like this of just putting a positive integer in like square brackets and using that to denote all of the integers from 1 up to that integer. It's very small, but it saves you having to write out a lot of commas and dots, and this is something I plan to use a lot, like moving forward. Like anytime I need to write indices like this, I want to use this notation because it's really nice. But anyways, so let's talk about the contents. So first of all, they define factorization machines as defined in the previous paper, and here this equation, as we can see, it was the equation that was used in the previous paper for pairwise interactions. And I guess this is a little bit confusing with the choice of variables here because in the previous paper, lowercase d referred to like how many interactions you were considering. So that is a little confusing, but it won't be a big deal here. But anyways, they say a few things here that aren't as important. But then they go ahead and they define higher order factorization machines. And they define it like this. So it's, you have the dot product of W with X, which makes sense from before. Then for each, and you have a bunch of sums that goes up to whatever the mth order is. And you have the sum over all indices from, like for the m term, we have the sum over all indices j1 through jm, where j1 through jm are positive integers that satisfy these inequalities. So jm is greater than jm minus 1, which is greater than all the way down to j1. And of course, these all, where do these ji's belong? They have to belong to n because, oh wait, no, it's called d, lowercase d in this paper. So this is the j1 through jm, these all belong to d. And it's this sort of operation on the rows of the matrix P times all of the x's. And so here we see this sort of like generalized inner product between these rows is defined as the sum of element-wise products. So let's make sure we understand that. So basically we take all of these rows and we take the element-wise products. So we will take like the first, let me just write out an example. So A1, A2, A3 times B1, B2, B3. If we use this circle as element-wise product, so this is just going to be A1, B1. Let me put commas here to make it more clear. A2, B2, A3, B3. All right, so we just go through each, so these vectors need to have the same size, and we just go through each coordinate and multiply the entries together. And then when we take the sum, we just sum all of these together. So what you can see here is that like if you only have two vectors, then you're just taking the dot product, because you'll take the element-wise products and then add them together. That's just the standard dot product. But this notation allows us to do this operation more generally. But we should make sure that this this equation 3 here matches what we have from the previous paper, because if we look back at the previous paper, what do we have? For higher order factorization machines, here it's called D-way factorization machines, whereas in the new paper it's lowercase m is used to denote how many orders you're considering in higher order factorization machines. So we have this sum here. All right, so let's check this. So we have, so here the W0 does not appear in the second paper, but we don't really care too much about that. And basically what we're doing here is we're taking the sum from L equals 2 to D of this thing right here. And so these things here that are within this sum from L equals 2 to D, each one of those should correspond to one of these sums that appears here. Because here we see we have the, so comparing to the previous paper, this is the D equals 2 term, or no, it was lowercase l. So this was the L equals 2 term, then this would be the final L equals D term. All right, so basically we should check that the terms that look like this single sum here match the terms from the previous paper, which I just closed because this application is annoying. So I'm going to write it out for you because I have it handy here, and because we're about to use it. So let's take the case of we're going for a particular L. Let's just choose some L in the previous paper. So we have the sum from I sub 1 equals 1 to n. And then we have sum from I2 equals I1 plus 1 to n, all the way up to the sum from I sub L equals I sub L minus 1 to n. Then we have the product from j equals 1 to L of xij. And then we multiply this by the sum from f equals 1 to k sub L, the product from j equals 1 to L of Vij, comma f. I'm just going to write this without the comma. So Vijf, and then we have the L up here. I'll put the comma in here. Okay, so we have this sum. So this is the L term from the factorization machine equation from Rendell's paper. So this should correspond to the same term in this paper, but for L. Okay, so let's write this out. And let's try to derive this. So this is going to be equal to what? So I have the sum from, and I'm switching to J here for no apparent reason, but just, of course. I'm switching to J here because this step, all I'm doing is I'm matching the notational uses of the newer paper. So instead of indexing by i's, we index by j's. Instead of going up to n, we go up to d. So we'll go, and we finally end with a j sub. And now here we're going to go with L again. JL equals JL minus 1 up to D. Then we'll have the product from T equals 1 to L of X sub J sub T. Right? Because we're just replacing this J with a T and we're replacing this I with a J. Right? Times of the sum from S equals 1 up to K sub L. We're still using that notation. Product from T equals 1 to L of P J T comma S. And this corresponds to, no, not M, it's to L. I wrote this as M in my notes, but it should be L. That's why I'm getting the confusion. Okay, so now what is this equal to? And to make this a little easier on myself for writing, I'm gonna give myself a little bit more space. So this is the sum over all Jm greater than J1. Now, first of all, does this make sense here? So basically what we're doing is we're replacing this sum with this sum. So here, what we're doing is we're taking all, so when we take this entire sum, or this collection of sums, J1 will go from 1 to D, and so on and so forth. Basically what we're doing is, what needs to happen here is each of these, when you get to the end of all these sums, you're going to have some combination of integers from J1 through JL. And we know that these are all going to be between 1 and D. And we also know that this is going to be an increasing sequence because Ji starts at Ji minus 1 plus 1. Which, let me write that out. So Ji starts at the previous J plus 1. And so that means that the sequence J1, J2, J3, etc., this will be an increasing sequence. And so basically, and also for every possible sequence of integers, so we're going to get L integers here. These integers will be increasing. They will be between 1 and D inclusive. And for every possible collection of integers that satisfies those conditions, it will appear exactly once in the sum. Because the way because ji begins after ji minus 1, you don't get any repeats. So another way of writing this is we're just taking the sum over all sequences of integers, all sequences of L integers, which are strictly increasing and are between 1 and d. And that is exactly what we mean when we write this equation, or when we write this thing under the summation here. Sum over this stuff. Right, so this is just a different way of writing this in a way that's a lot easier to write. All right, and then we still have this this product here. We're not going to change this at all. Product from P equals 1 to L. I know it's not good practice to change your notation conventions, but I'm going to do it to make our lives easier. And then we're going to multiply this by this. We're going to take the sum. Now, what are we taking the sum over? So let's just write it out and then understand why this works later. So we're going to take the sum from t equals 1 to, or the product of p, j, t, 1, comma, L, all the way up to here. T equals 1 to L, p, j, t, comma, k sub L. Then we have this L. Okay. So basically what we're doing is we're summing, so we're thinking of this as a vector which has k sub L elements. This is the first element, and this is the k sub L element. And so we're just summing up all of the entries in this vector. And if you look, each entry in this vector corresponds with one of the each entry in this vector corresponds with one of the terms in this sum, because we're taking the sum from s equals 1 to k sub L of this product. And when you take this product and you sub in s equals 1, you get this. When you sub in s equals 2, you'll get the next one. And then when you eventually sub in s equals k sub L, you will get this one. And so this is just a different way of writing this sum. Okay. So now what do we do? So now this is equal to the sum, and we're again taking j sub L, we have to j sub 1. I have this product from t equals 1 to L. L's are always a tricky variable to use. And now we're going to multiply by the sum of, now another way to write this is like so. pj1 all the way up to pjl. Okay, and why is this true? So, this is a vector, and this is a vector, because basically what we're doing is we're taking element-wise products. So what is the first entry of this vector going to look like? The first entry of this vector is going to be the product of the first entries of all of the vectors that appear in here. And the vectors that appear in here are row pj1, then row pj2. By row, I mean the row of the matrix. So the row vector pj1, the row vector pj2, all the way up to the row vector pjl. And the first entries of those vectors are just it will be lowercase p sub j and then the index I, comma 1. So the first entry of this vector is lowercase p sub j1 comma 1. Then the next one, or the next vector that appears here, the first entry will be lowercase p sub j sub 2 comma 1. All the way up to here, and eventually what you end at is you have lowercase p sub j sub l comma 1. And we see that that's exactly what this product is here. I wonder if it would make sense to write this a little bit more. So this is pj1 1 l, pj1 2 l, all the way down to pj1, and then no, I'm putting this in the wrong place. All the way down to pjl 1 l. It's going to be this as a vector. Then this, I'll put the second one as well. pj1 2 l, pj2 2 l, pjl 2 l. Then eventually we get over to pj1, and then this will be the final one. No, I have flipped it to, because this is the row pj1, so it's going to have a pj1 everywhere, and this is going to go down to, should go down to D, right? Because there are, no, it should go down to K, because P is, it should go down to KL. So this will be J2 1, J2 2, J2 KL. This is PJL 1, PJL 2, L, L, PJL K sub L, L. Okay. So now this makes sense. It's a little confusing here because these are row vectors and I've drawn them as columns. But because they're row vectors, that's why the first entry in these lowercase p's stays constant while the second entry increases. So this equation is the sum of the pairwise products of these vectors. So what is the first entry? So when we do the pointwise products of these vectors, that's going to give us another vector of size KL at the end. And so what is going to be, what are going to be the entries? So that the first entry is going to be this times a bunch of other things times this. So it's going to be pj1 1l times pj2 1l all the way up to pjl 1l. But that's exactly this product here. And then similarly, pj1 2l times pj2 2l all the way up to pjl 2l is going to be the second entry here. And then finally, pj1 kll pj2 KLL, pjl KLL. We're multiplying all of these together, and that's exactly what this multiplication is. So this vector is exactly the same as this vector. All right, so these things are the same. But now, remember, what is this? This is precisely the sum for all JL greater than J1. We have all of this stuff from before, which hasn't changed. And now this sum, remember, by the definition, this sum is equal to this sort of generalized inner product. So this is PJ1 L, and then that goes all the way up to PJL row vector L. Okay. And this is exactly equation 3. Or this is exactly the L term of equation 3. And so it's a bit messy, but this is just to confirm that the notation in equation 3 matches the notation from the previous paper. So this confirms that we're all on the same page, and it confirms that this notation is valid. Okay, so this is a definition. So what do we do with this?